Hello everyone, my name is Artem Mavliutov, and today together with David we are gonna present to you the numerical model of Boltzmann-Nordheim equation. The Boltzmann-Nordheim equation describes the time evolution of a gas. When this gas is formed by bosons and is cooled down to a low temperature, we can observe a Bose-Einstein condensate, which is one of the most striking phenomena in nature. The study of this equation is still undergoing and can bring us closer to an understanding of this quantum effect. We are interested in a distribution function, which is potentially written in 7 dimensions: 1 dimension for time, 3 dimensions for space, and 3 for velocity. Therefore, discretizing such an equation, even on coarse grid, requires huge computational resources, as well as parallel algorithms. The form of this equation is given in this slide. Basically, it has 3 components: time derivative, the transport part, and the collision term. In order to discretize this equation, the simplest approach is the Lie-Totter time splitting, in which we solve separately the transport part and subsequently the collision part with the initial condition of the solution of the transport step. In the next iteration, the transport part is solved with the initial condition of the solution of the collision step on the previous step, and we iterate. The numerical methods used are the following. The transport part is solved using finite volume method, the collision part with the spectral methods, and the boundary conditions are imposed as in the presented paper. The initial conditions are classical Maxwellian distribution coupled with the smooth cosine function, and the boundary is periodic in space and in the velocity. The parallel implementation of the transport equation consists of parallelizing the for loop, and this is done with the OpenMP library. In the end, we have obtained the time evolution of the distribution function, which was written in 5 dimensions, 1 for time, 2 for space, and 2 for velocity. The animation shows the distribution function integrated in space and projected on the velocity domain. As you can see, the equation is discretized on a very coarse grid because of the high computational cost of the collision operator. Therefore, it is important to parallelize the collision operator, and this was done by my teammate. Over to you, David.
As Artem said, the term that slows down the computation is the collision term Q. Q is short for a sum over 6 terms, where 2 of them describe the classical collision term and 4 additional terms describe the collision with quantum effects. The 2 classical terms are very similar and fast to compute, but the quantum terms are trilinear, which makes them expensive to compute, especially Q1Q. This is the time cost for an example on a grid of size 16 × 16 up to 128 × 128. The cost of the serial computation of Q1Q behaves like n to the power of 4 times the logarithm of n, where n is the grid size. And it's getting even worse when computing a 3-dimensional example. My task was to implement an improved version of the computation of Q1Q using a new communication pattern to reduce the time cost on each process. The key idea is to split the MPI word communicator in 2 ways. Assuming that the word communicator consists of s times s tilde processes, we split it along the lines and along the columns. For the line communicators, we then get s communicators with s tilde processes. Along with these new communicators, 2 key challenges arise. At first, I need to redistribute the data such that every process gets the data it needs. Here we can take advantage of the fact that the line communicator and the row communicator overlap with each other. The second challenge is to adapt the computation of Q1Q. The main goal here is to avoid a large loop over the whole domain, as in the old computation. Eventually, it resulted in a so-called hybrid method. I compared it with the classical implementation on a grid of size 64 × 64 with an increasing number of processes. We are very happy about the result, as we can see that the new method is faster and scales better. Nevertheless, we want to improve the result further, as we will try to improve the speed and the spectral accuracy of the computation. At the end, I was able to run the simulation with the improved computation of Q1Q. Here you see the distribution of particles with an initial Maxwellian distribution.